I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics: Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. Each of you is making good progress with analyzing each of your variables on your final project. I'm pleased about that. Today, we're making a big shift in the course, but this is like the final lap, what we've been working towards all session. It's called simple linear regression. Basically, up until this point, we've been learning all of the tools needed to do what's called regression. What we're going to start with is the simple linear regression. We're going to look at this idea called models, and you'll hear this a lot, especially in statistics, but also in your sociology courses, where they'll talk about, well, what's your model? Or your model is not specified correctly. What a model is basically a mathematical equation that describes your data. We're going to be learning how to construct and interpret mathematical equations that describe our data. In particular, we're going to look at linear, which is just a straight line type of model. So that's, once you figure out how to do this, you'll be able to finish your final project, and this will mark the end portion of the course. To illustrate how we look at linear models, I thought it would be appropriate to think about how we could predict exam scores. So can we predict exam scores by looking at your homework scores? So you have two quantitative variables. You have exam scores, which is a quantitative variable, and then homework scores, which is a quantitative variable. And can we use just the information we have on your homework scores to predict what you'll get on the exam? So I've taken data from a previous class, where you look at the x-axis is your homework scores. It ranges from 80 to about 200. And then we have data on what the students got on their exam. And this is a scatter plot of that. So basically, the person who had an 80 as their homework score ended up getting a 55 on the exam. This is our data that we're working with. It has a sample size of 7, and we're going to use this information to create a linear model. And so our dependent variable is the exam score. For your final projects, some of you, the outcome that you're interested in is happiness, or should the government help the poor, or views and attitudes about abortion. So your dependent variable is the focus of the study. That's what you're wanting to predict or understand more about. And then the independent variable is associated with your outcome. So your outcome is exam score, so is homework associated with what you get on the exam score. And some of you might find out or see that actually homework is not at all associated with exam score, or there could be another variable that's not at all associated, but that's what we're testing to see. The scope of this process is the idea of fitting a model to help us predict students' exam scores based on their homework scores. So you'll hear the term, what's your model, or what's the best fitting model? A model is a mathematical equation that describes this relationship. We use mathematical models, like an algebraic equation, to describe the relationship between a dependent variable and an independent variable. And a linear model is a specific kind of mathematical model that is used when the relationship between x and y is linear. So again, generally speaking, there's a bunch of different types of models and different equations, forms that you can use to describe relationships between data. And we're going to start with the simplest relationship, where it's just a straight line. As the x value goes up, the y value either goes down or goes up. That's what we're referring to when we say a linear model. Y is a linear function of x. And if you remember from algebra, there's a reason why you had to learn algebra. It's so that you could do statistics, but more so that you could analyze data and make sociologically informed predictions and discussions about data. And so the algebraic formula is y equals a plus bx. So you still have your variables. Y is your exam score in this situation, and then x is the homework score. And I'll explain how we get a and b. This is the equation we'll use to describe the data that we have. The formal name for it, or what you'll hear a lot, is regression equation. A simple linear regression, which is this, because it's a linear relationship, describes the relationship between x and y. And the important thing is that it can be used to predict values of y when x is known. The main reason why we're trying to fit an equation to our data is so that in the end, we can actually use that equation to predict future values. So in a sense, with the data that we have, I already know what the homework score was and what the exam score was. So it doesn't really help to be able to predict an exam score that already occurred. But what I'm interested in doing is predicting what your exam score will be, because you haven't taken the exam. I have your homework scores, and I want to make a prediction just based on your homework scores what your exam score will be. And I'm going to use data from past classes to make that prediction. Do you think I'll be successful at it? You can see when we get the outcomes of the exam, we'll see how well our model actually fits the data. So what we're going to do is create a simple linear model that can predict exam scores as a linear function of homework scores. So there's two ways of doing it. Visually, just eyeballing at what's the line that goes through the data, and then mathematically, what's the mathematical equation associated with that line. So the line that we're thinking about, we have a regression equation. Also related to that is a regression line. The goal is to find a straight line, y equals a plus bx, that best fits the data in the scatter plot. So in a sense, visually, you could draw a line, and you want to sort of pick a line that best fits. It's sort of like my 4-year-old kid, if I want to do connect the dots. It isn't really like connect the dots, because if you did that, it'd be a jagged line all the way through. But if you want to just pick a line that cuts through the center of all your data points, that's what the regression line would be. So you can envision like an infinite number of ways to draw the line. You can do it through eyeballing it and see, yeah, there is potential for a line to cut through all the data points. But in the end, we're going to need to do it mathematically. So we're going to have actual values and predicted values. The actual values are the y values, like right here, our data point y. It's the value of the dependent variable of a particular participant. So this participant had a 105 on their homework score, and they got a 63.5 on their exam. So that's an actual value. That's real data that we have that's in our data set. And then the predicted value is y hat, and that is the value of the dependent variable that would be predicted for a given value of the independent variable. So we've drawn this line to say this is the relationship between x and y, and if we didn't know a person's exam score, all we knew was their homework score was 105, we would predict that their exam score was 61.8. So this is what the actual score was. This is what we would have predicted based on the regression line that we created. It's important to know the difference between actual values and sort of these predicted values. In linear regression, the predicted values fall on the regression line directly above the value of x. So we're saying that this is the estimated relationship between x and y, and So the predicted values are going to be the values that fall on the line. Don't get them confused with the actual values in our data set. And in fact, like with this person, their score doesn't miraculously change to 61.8. It remains the actual value. You just know what we would have predicted was a 61.8. The best fitting line is the one that makes the predicted values closest to the actual values. So when we're trying to fit the best line through these data points, we want to find the line that makes the distance between this point and the line the smallest for all of these. Right here, the line fits pretty well in relation to this data point, but less so for this data point. And so collectively, we want to find a line that fits all the dots in the best way possible. So a term that will come up is something called residuals. This is a fancy term that actually has a fairly simple idea behind it. So the residual for each data point is the actual value minus the predicted value. The y is the actual exam score from our data set, and the y hat is the predicted value based on the regression line that we're creating. So a way to look at it visually is you have y, which is the 63.5, minus what we would have predicted the value of y to be, 61.8, equals 1.7. That measures the distance between our data point and the actual line, where it would fall on the actual line. And so it's the vertical distance from the point to the regression line. And so you could calculate the residual for each of our data points. The regression line becomes a better fit as the sum of residuals decreases. You know, we could have started with a line that cuts like this way or something, just randomly put that down, and we would calculate the residuals and they'd be really large, because if we had a line like this data point would be way off the line and so forth. And so a better fitting line is one that can, again, reduce the sum of all the residuals. In the process of fitting the model, finding a regression line that best fits the data points, we need to find the regression line or the mathematical equation that provides the smallest sum of the residuals. So this is a fancy process of what it's going to do to find the smallest sum of the residuals. Basically, we're going to add up all of these residuals and find out what line would give us the smallest sum of all the residuals. So we have many different options for lines, and we want to find the best line. The way we do that is through a process called least squares regression. Least squares regression is an algorithm that chooses the regression line that minimizes the sum of the squared residuals. So there's probably 10 words in here that you never use in your everyday language. But I'll walk you through what that means.
Well, how you say that one word?
Algorithm?
Yeah.
A way to understand algorithm is it's a routine. So I'll use basketball as an example. If you want to be a better free throw shooter, there's a routine you go through. So when Chelsea gets up to the line, she probably has a routine that she goes through. She goes through step 1, step 2, step 3, step 4, and if she repeats that process each time she gets to the line, she's going to make the basket, or hopefully. And fortunately, a computer program does this for you. So you don't have to go through the process 100 times. The computer program does it for you. And the formal name of the process is called least squares regression. But the goal is, think of our data points, finding a line that sort of best cuts through all those data points. The formula for this is right here, and we'll just focus on this half. So y is our observed value for each of the respondents. So we have 7 different y values. And then the y hat is the predicted value based on where it would fall on the line. And then the reason why we square it is because imagine if some of the data points were above the line and some of the data points were below the line. If you measured above the line, those would be all positive numbers, and the data points below the line would be negative numbers. And so they would cancel each other out, but by squaring it, make sure that all of them are positive numbers. So when you add them all up, you're going to get what's the sum of the residuals. And what the algorithm does, software programs can take your data and run every combination of y's and y hats fitted to a regression line until it finds the line that produces the smallest value for the equation above. In a sense, y hat is calculated using that equation, y equals a plus bx. The a value and the b value, you can change those all around to make different lines. What the software program does is it tries every line possible in that regression until it finds the line that provides the smallest amount of residuals in the data points. At the end of the day, the computer will find the best fitting line for you, but it's helpful to know what it's actually doing. Here's visually what's going on with least squares regression. So it takes each of these data points and it calculates, for a particular line, it calculates the residuals, the distance between the data point and the regression line for each of your data points. As I explained, the residuals need to be squared because some of the values will lie above y hat, leading to a positive number, and some of the values of y will be below y hat, leading to a negative number. So that's visually, it would do that for multiple different types of lines that you could draw. The regression line equation is what we're going to be using. Like, it's not particularly helpful to just have a line on a plot, but you want to know what's the equation behind that line. And the equation for the estimated regression line is in this form, and it's very similar to the algebraic equation that we looked at. You notice you have y hat, and instead of a, you have this formal thing called b naught, or beta naught, and then beta 1 times x. But you can think about it in simplistic terms as y equals a plus bx. But in statistics, they're going to use this more formal notation. So beta naught, it's the Greek letter beta, and then for 0 they call it naught. So you'll refer to it as beta naught, and it's also the intercept. The intercept is the value of y hat when x equals 0. So if you were to, in a sense, plug 0 into this equation, you'd see that y hat equals beta naught. And that gives you your intercept. And then the second one is beta 1, which is your slope. So as beta 1 changes, it's going to change the slope of your line. The definition of a slope is the factor by which the value for y hat increases for each unit increase in x. If you think of a slope of a line, as you increase the values of x, the values of y are going to increase at a certain rate. It all depends on what this beta 1 value is. This is a very elaborate explanation for what a line means. Like if you have a line in a data plot, this is a mathematical way of describing that line. And then in statistics, the term that you'll hear a lot that will come up is a term called coefficients. Again, another term that we rarely use in everyday language, but you'll hear it a lot in sociology of what are your coefficients? Or what are the values of your coefficients? Is your coefficient significant? Is it in chemistry too? Okay, so Tim already knows what coefficients are. So we will be asking, are your coefficients significant? What are the values of them? And what they're asking is basically, what is the value of beta naught? What is the value of beta 1? And so on. So that's what coefficients refer to. Like I said, the computer will generate the regression equation for you, and it will give you a particular output. But you need to know how to interpret the output. So it almost sort of look like this, where you have coefficients, and it'll say intercept, or it'll say like beta naught, or it might say the particular variable that you're working with. And then it'll say slope, beta hat 1. And then it gives you estimates for each of these values, and it also gives you a standard error. So does this look familiar to other things that we've done where you have an estimate and you also have a standard error? There's sort of a connection between what we've already done and what we will be doing. To look at this, we have predicted score is y hat, and then beta hat naught is going to be 37.69 plus we take our beta 1 hat value, 0.23, and we multiply it by homework score. We start with our general equation, and then our computer gives us a specific equation for our specific data set. It basically says the line represented by this equation is the best fitting line for our data. A way to interpret this equation is saying that for each point increase in the homework score, the predicted exam score will increase by 0.23 points. If we take a homework score, and if you add 1 point to it, we predict that their exam score will increase by 0.23 points. And I'll walk through more specifically what that looks like. Before we look at it and try different examples, I want to talk about units because, again, it's important to know what's the units of what we're working with, because a lot of times you or others will give answers and you just give a number. Like we said, mean income is 10.2. What does that mean? We need to know, well, what are the units for that value? And so I'm just going to map out what the units will be for this equation. Y hat is going to be the units for the y variable. Beta naught is going to be in the units for the y variable. And x is going to be in x units. And beta 1 is going to be y units divided by x units. And so then specifically what that would be for our equation is going to be exam points. That's our y value is exam scores, and so you want to know exam points. The units for this is exam points. The units for this would be homework points. So like if we said an increase in 100 of homework score would be an increase of 100 homework points. And then the slope is going to be, the units will be exam points divided by homework points. And so in a sense, if you do homework score times the slope, you'll notice that homework points and homework points cancel out so that your ending units is going to be exam points. Now that we have our regression line and our regression equation, we can use this information to predict what your exam score will be. So the regression equation can be used to predict the value of y for a given value of x. And so we have our predicted exam score equals 37.69 plus 2.3 times the homework score. So if I know a student's homework score is 140 points, my best prediction of his exam score, so this is pulling away from the data. Let's say I take one of your homework scores, total homework score is 140 points. My best prediction of what the exam score will be is I take the formula 37.69 plus 2.3, and what I'm inserting is the known homework score of 140. And so then the predicted exam score would be 69.9 points. And this is how the regression equation can help us predict what exam scores will be, or whatever the outcome we're interested in. So visually what this would look like is we have our regression equation, and so this is key. Throughout I'll be asking you, well, what's your equation? What's the regression equation that you're working with? Because that allows you to make formal predictions. So it takes the y-score and finds out where it hits our regression line, and then the corresponding x value that's associated with it. And so you can do it visually and see that, yeah, it's around 70, or you can do it mathematically and find out that it's actually precisely 69.9 points. The actual data point would be 140 and 69.9. So the interesting thing with this is that not only can I predict what your exam score would be, but I can also say for each additional homework point, we predict that the exam score will increase by 0.23 points. So say the next student that I look at had 150, then I know that my predicted value for their exam score will move up this line at a steady rate. That's where the slope comes in. It basically says for every 1 unit increase on the x-axis, we have a 0.23 unit increase on the y-axis. To bring it back to sociology and specifically your final projects, as we've been talking about independent variables and dependent variables, unlike correlation, for linear regression, it matters which variable you select to be your independent variable and which variable you select to be your dependent variable. Like with Chris's example of should the government help the poor, that's his dependent variable. And one of his independent variables is income. And so we're using income to predict whether the government should help the poor. It would be a different equation to say, can a person's attitude about helping the poor predict income? So in our example here, when homework score is the independent variable and exam score is the dependent variable, this is the regression equation. However, if you flip it, when the exam score is the independent variable and the homework score is the dependent variable, this is what the regression equation would be. Because basically we're switching it to say we're going to use information about the exam scores to predict what homework score is. And actually you can see where that doesn't even make sense to set up your model that way, because what we have is homework scores and we want to predict exam scores. Because once you have the exam scores, you already probably know the homework scores. But all that to say is the order of what your independent variable is and what your dependent variable is matters when you're doing these equations. That's why probably I've been harping on you to identify what's your dependent variable and get really clear on what your dependent variable is, and then we'll build independent variables around that dependent variable. An example, if a student, so this is one that you guys are going to work on. If a student has a homework score of 180 points, what would be our best prediction of her exam score? No, I'm not going to make you do it. So, because you don't have the equation in front of you. But it'd be 80 points. And the way we find it is, again, this process of take our regression equation, and the value that we need to enter in is the homework score, which is 180 points. And if you calculate it out, it's going to be 79.1, and that should say points. Again, you can take any homework score. So I could literally go through my grade book and I could pull out each one of your homework scores, plug in the value in here, and find out what my prediction of what your exam score would be. And so an important thing to again bring up is the intercept, which we talked about briefly before. The intercept, which is 37.69 in this equation, tells us what the predicted exam score would be when a student's homework score is 0. So if I wanted to predict what a person's exam score would be if their homework score was 0, do you think this would be a good prediction to make? You'd say a homework score of 0, so that cancels to 0, and you'd say the predicted exam score would be 37.69. The range of information that we have is students who have basically between 80 and 200 on homework scores. We have very little knowledge of what the outcome would be if you had a homework score of 0, because we have no data, past data, with people who have homework scores of 0. So we simply don't know. And the way that I would say it is, thankfully, none of the observed homework scores are anywhere close to 0. So we have no way of knowing if the linear trend continues all the way down to 0. So in a sense, this is a linear relationship for the range of values that we have. We don't know what happens when the homework scores drop below 80. It could, just like what Brittany's suggesting, is just plummet straight down to 0. But the main point is that we don't know, because we don't have any prior knowledge of people having 0 homework score and what they would get on an exam. And again, to remind you of what residuals and how they fit into this, if you wanted to know what is the residual value associated with the observed data point 105, 63.5, the way you would do that is, again, using the regression equation. We walk through and you have 61.8 points, and then the way you calculate the residual is you take your observed y minus the predicted y, so you can calculate what the residual would be for a particular point. And this is important for further on in the course, where we use that value to make estimates for our model. But this just shows you how you would calculate or find mathematically what the residual value is. In predicting exam scores, if I was going to say, here's another data set from a prior class which basically took exam number 1 score and exam number 2 scores and looked at the relationship between what you got on exam number 1 and how it's associated with exam number 2. And this is the regression line associated with that. And so because you guys don't know what your homework score is, I thought I would give you this equation if you're interested in predicting what your score on exam 2 would be. And so I want you individually to predict your exam number 2 score and just keep it to yourself, and we'll see how well the prediction is. So in a sense, it shouldn't necessarily be higher, but what it's saying is that higher scores on exam 1 will lead to, on average, higher scores on exam 2. But what you're noticing is that, on average, people did poorer on exam 2, so all of the exam 2 scores are shifted. So if you're a little bit concerned, or you're like, wait a minute, this is destiny, this is what my exam score is going to be, one thing to note is that outliers can affect the slope of the regression line. So this particular student who did great on exam 1, got an 80, bombed exam 2. And that 1 point on this scatter plot is pulling down this line for the entire class. And maybe, let's say this student was super sick and just had extenuated circumstances, and let's say we pull them out of the data set, this line would then shift up, and in a sense your predicted exam score for exam number 2 would actually be higher. So you want to be aware that outliers can affect our predictions for the entire class. More importantly, this regression is using only one variable, your score on exam number 1, to predict your score on exam number 2. And really, to improve our prediction, our regression equation should include other variables associated with exam performance. So if I was only using your score on exam number 1 to predict your score on exam 2, that wouldn't necessarily be a very good prediction because there's other factors. So if I did homework score, exam score, what other factors affect exam performance? Sleep. So I could sort of be asking you guys, how much sleep have you gotten last week or the night before the exam? Yeah.
How many hours you studying?
Exactly. How many hours you study. So what you guys are doing is you're building a model that's a more comprehensive model that will give more information and ultimately provide a better prediction. This is a weak model because I'm only using one variable to predict exam score. And so in the same way with your final projects, that's why you have your one dependent variable that you're interested in knowing about, but then you're thinking sociologically, what are the factors that are most important or most associated with that dependent variable? So it isn't just picking random variables that might or might not be associated, but it's what does sociological theory suggest are the most important factors associated with happiness, attitudes about abortion, or whatever. So there's 4 cautions that you need to be aware of when doing regressions, and I'll walk through each of them. The first one is out-of-range predictions, and so that's what Brittany alluded to. Don't use the regression equation or line to predict values outside the range of x values available in your data. So you can't really extrapolate. So you can't say, okay, the line's going in this way, and so when we go off the charts, like with a homework score of 0, let's just extrapolate and pretend that the line just continues in the same direction. It's a caution. You really shouldn't do that because you're making judgments about things that are not known. And also, another related to this, if none of the x values are anywhere near 0, then the predicted value at the intercept is meaningless. So again, it's the same idea that we do have an intercept value, like where does the line ultimately intercept the y-axis, but a lot of times that actual point is way out of range, and so it doesn't make sense. Like I think one of them is, oh yeah, if you use regression like age, all of our data points are between 18 and 82, and you want to know how age is related to income, and if you said, well, what is the income at age 0, it might say $3,000, but you'd be like, wait a minute, that just doesn't make sense. Or it might say negative $10,000. But the point is we only have data on people between the ages of 18 and 82, and so we can only make predictions about people within that age range. Then the next one is nonlinear associations, and you guys have found this to be true. Computers will calculate a regression line for any 2 variables, even if the 2 variables are not quantitative. So some of you have been putting in two categorical variables and you say, hey, the correlation is 0.68, and that's sort of describing the regression line, the computer will follow the procedure no matter what you put into it. So you need to make sure that the variables that you're looking at are quantitative. So think categorical variables don't work in creating a regression line. The computer will also calculate a regression equation even if the two variables are not associated. It just takes the information and runs the algorithm and creates the equation. And this is related to what we talked about of confounding variables. So I think what we watched like the first week of class, the video on ice cream being related to polio, they took all the data points and threw it in the computer and it said, wow, look at this relationship. But in reality, there wasn't a relationship. It was confounding variables that were driving both of those factors. And then another with nonlinear association is that the association between the variables is not linear. So there might be an association between the variables, but it's not a linear association. And so one possibility is that it's a curvilinear relationship. And what we talked about, age and income, sort of at younger ages, income is low. And then as you get older and into your midlife, income is at its highest point. But then as you get older and go into retirement, income drops down. And so the relationship is not a straight line, but it's a curving relationship. And if you had that, the best fitting regression line would be right through the center. And I think we did an example of that where it cancels each other out, and so it would imply there's no relationship, when in actuality there is. So it's important to sort of plot your data or look at your data to see visually what type of relationship you see. And so ultimately, the regression line should only be used if the association is approximately linear. You guys can chop up your variable so that it serves you. Like you're looking at religion and you're interested really in the difference between Catholics and Protestants, you can eliminate from your analysis all the people who aren't in either of those categories. Or like if you're interested in attitudes about abortion for people under 30, you can constrain your data to just people under 30. So don't feel like you're bound by, well, the variable has all this extra information in here. The variables serve you in your analysis. Regression caution number 3 would be outliers. And again, we looked at that. Outliers, especially outliers in both variables. So like, say we had someone in the class who got a 0 on the homework score, but then got 100 on the exam. That would really throw off our analysis because it would be such an obscure and unusual data point that it really wouldn't help us in making sort of an overall prediction. So when you're looking at your data, you want to just sort of be aware, are there any like extreme outliers? And plotting your data, and if you're interested, there's a little applet that you can click on for this to look at how outliers influence the regression line. And then the fourth and final caution is causal claims. And this is a critical one, and it's one that's often violated, is that even though we can use X to predict values for Y, this does not mean that changing X will cause Y to change. You're just making predictions based on the values that you have. And so an example would be, let's say you went into my computer and increased your homework score to 200. This would not cause your exam score to increase. So all this equation is doing is describing the relationship. And so if you went in and changed your value of X, that wouldn't sort of miraculously cause your exam score to go up. While there might be a strong association between homework score and exam score, there are confounding variables, and like the ones that you guys mentioned, like amount of time studying and so forth, that are associated with both scores. Really, what's behind this relationship between homework score and exam score is how much sleep you're getting, how much you're studying, all these other factors that really influence both how well you're doing on your homework and how well you're doing on your exam. Causal claims can only be made if the values of the independent variable were determined randomly. And that's where we talked about experiments, where if somehow I randomly assigned how much sleep you could get during the course of this class, then I could make a causal prediction that amount of sleep affects your exam performance. This last point is sort of a key one, that despite the causal claim caution, The fascinating thing about what we're doing here is that because of the strong association between homework score and exam score, we can still use homework scores to predict exam scores. And this is a critical thing. You guys had rightly said that just looking at homework scores would be maybe a poor predictor of what exam scores would be. But if you think about it, the thing that influences your homework score, like sleep and study and all of that, probably has the same relationship with your exam score. So actually, even though homework score might not be like a great measure, because it's strongly associated with exam score, we can actually use that without even knowing how much you sleep or how much you study. I can actually take your homework score and make a pretty good prediction of what your exam score would be, even though, in a sense, homework score in and of itself doesn't cause difference in exam performance. The things that cause homework scores to go up or down is going to be the same things that cause exam scores to go up and down. And so that's why, even though we can't make causal claims, we can make really good predictions. And that's the value of all this, because a lot of times you could say, well, gosh, if we can't make any causal claims, why do we do any of this? And it's basically because if we have the right variables, then we can actually make good predictions. Even with me not knowing how much you study or all these other things, this is such a strong association that I can actually make a good prediction. What we did up until this point is looking at a specific sample and how do you make predictions out of that. And so the goal of this course is learning how to make inferences from our sample to the whole population. Again, we're using simple linear models to make these inferences. And the first is the simple linear equation based on our sample data is where we have y hat equals b naught plus beta 1 times x. And this, it's an estimate of the relationship between x and y. And another way of thinking about it is that beta naught and beta 1 are sample statistics. Does that sound familiar? We've taken data from other samples and calculated sample statistics. What are some other sample statistics? X bar. Yeah, that's another sample statistic. We've already sort of calculated a bunch of sample statistics. And in fact, with our homework scores and exam data set, we could find out what X bar is, what the standard deviation is. And so there's statistics that are pulled from our sample. And so in the same way, beta naught and beta 1 are sample statistics. And it's important to sort of link those two together, that just like the mean score for our homework data set, we can calculate that. We can also pull from our data set what beta naught and beta 1 would be. So we treat them just like we would any other sample statistic, even though it's not nearly as intuitive as the mean or the proportion, but they're treated the same way. Just like we would take a sample statistic to find out what the population parameter would be, we have our simple linear equation to find out what our true simple linear equation for the population is. So this is our estimated relationship, how x is related to y. And I say true here in the sense that if we had the opportunity to sample the entire population of all students taking Soc 132B, and we put all the numbers into the computer algorithm, this would be the true simple linear equation for the population. Does that make sense? We aren't able to gather data on everyone, so we took a sample of people, and based on the sample, this is the equation that we came up with. And if we were going to pull from the entire population, this would be the equation. And the error term basically is accounting for errors in our model, which we don't need to go into, but it's what differentiates this equation from this equation. This is for the sample data, and this is for the population. They're basically the same except for the error term. And so it's the true relationship between x and y. And again, if you walk through the equation like we saw before, the slope of the relationship is beta 1, the intercept is beta naught, and then this is the random error. And so beta naught and beta 1 are the population parameters. So just like we had p hat for the sample proportion and p for the population proportion, we have beta naught hat is the sample statistic for the intercept, whereas beta naught is the population. The way we're working with this is that beta naught and beta 1 are unknown. They're unknown population parameters, so we're going to use our sample statistics to estimate what those would be. Just like we use a sample mean to estimate the population mean, we can use the values of beta naught hat and beta 1 hat to estimate the values of beta naught and beta 1. Does that transition from looking at a sample statistic like a mean and finding what the population mean is, it corresponds directly with these values for beta naught and beta 1. You might still be sitting there saying, but what the heck does beta naught and beta 1 mean? Well, we'll get into that more, but basically to understand that the process is exactly the same as how we did estimates with means and proportions. So using inference to estimate the slope. So again, inference, the two things we do with inference is confidence intervals and hypothesis tests. So it's the same two procedures that we've done throughout the course, but now we're going to be applying it to a more complex situation. It says we can calculate the confidence intervals and conduct hypothesis tests for the slope, which is beta 1, using the familiar formulas. Again, confidence interval is the sample statistic plus or minus t star times standard error. And for hypothesis tests, we have the t statistic, which is our sample statistic minus the null value over the standard error. And so again, that's probably why I've emphasized these are all sample statistics. So beta naught, even though you're thinking, what is that? Think of it in terms of it's our sample statistic, not the dependent variable. It's when you see a hat, it's basically referring to the sample statistic. It does get kind of confusing because sometimes you're just looking at your sample, but then sometimes you're making predictions. And both of them are estimations, so that's why they have the hat symbol. It means an estimation, whereas when it's capitalized and not italicized, it's true. So like P is the population proportion, whereas P hat is the little guy who's making an estimate of what big P is. So with this t statistic, use the t distribution with n minus 2 degrees of freedom. That's what you use for when you're doing this type of hypothesis test. So again, we have the population parameter, which is beta 1, and it's unknown. We have our sample statistic, beta hat 1, which is known. It's pulled from our sample. To remind you, beta 1 hat, it's the slope. It's that 0.23 increase in exam scores. So for every 1 point increase in homework scores, your exam score increases by 0.23. So it's the thing that sort of drives the relationship between X and Y. It's really important to know what beta 1 is because it's sort of the thing that enables you to predict what the outcome is going to be. And so the sample statistic beta 1 hat is our best estimate of beta 1, and we need to determine how much it varies from sample to sample. So just like we had sample means, and that was our point estimate, but it was only based off of one sample, and if we did 1,000 different samples, that sample statistic would vary slightly from sample to sample. So in the same way, beta 1 is going to vary from sample to sample. And so confidence intervals for our sample slope can be calculated using this formula. Before I do that, when we do confidence intervals, what is the simulation method that we could use to calculate confidence intervals? Bootstrapping. If we wanted to simulate the variation in sample statistics or beta 1s, we could do bootstrapping, or we can use the formula. And the formula is, again, the confidence interval, and then applied to this type of equation, our sample statistic now is beta 1 hat plus or minus t star times the standard error. And the confidence interval for b hat will provide the range of plausible values for beta 1. Like sample mean, we want to know what's the plausible values of the sample mean. We want to know what are the plausible values of beta 1. Our point estimate was 0.23, but we want to know how much would that vary from sample to sample. And so that's what the confidence interval will tell us. The specific way to calculate that, if we want to know the 95% confidence interval for the population, so we have our computer output, which gives us the intercept and the slope, and then we want to calculate the 95% confidence interval. At this point, we know what beta 1 hat is. It's 0.23. The computer will tell us what the standard error for that variable is, and then the only other thing we don't know is t star. And how do we calculate t star? Stat key. So we can do that. So t distribution, and the degrees of freedom are n minus 2. So our sample size was 7 minus 2. So the degrees of freedom would be 5. And then how do we find what the t star would be? So 2 tail. Okay. And then what would our t star be? 2.571. So the way of finding t star is the same for this process as it is for all the other confidence intervals that we've done. And so you plug in 2.57, and we get that the confidence interval is, for the slope, is 0.19 to 0.27. And what we can notice from this is that it's significantly different from 0. That actually homework score has an association with exam scores. The way we'd formally say it is that we're 95% confident that the population slope, beta 1, regressing exam scores on homework scores, is between 0.19 and 0.27 homework points per exam points. So for every increase in homework points leads to either between 0.19 and 0.27 increase in exam points. For tomorrow, we'll do conducting hypothesis tests. It's basically the same process that we've gone through with other hypothesis tests, which is the sample statistic, which is beta 1 hat, and you have beta 1, which is your null. In most situations, the null will say that beta 1 is going to be 0, and you set up the equation the exact same way. What we'll be doing tomorrow is looking at, we have a prediction, but then how much does our prediction vary? You have a point estimate for your what you think you'll get on exam number 2. We'll see what's our confidence interval for that point estimate, like how much can it vary from case to case. So that's all.